want to talk to you today about negaflops, which I bet you've never heard because we're going to coin that term today. And when I talk about negaflops, what I really care about here is the efficiency with which we run our computers, and particularly right now, AI. And we care about this because obviously there are the models that we're running today, and many of the wonderful things you've heard about today and we'll hear about later today, are all about harnessing a huge amount of computing power to do amazing things. But there's a resource implication of those. And so what I want to do is talk about some work that my lab has been working on for many years, and a particular piece of research that we collaborated with Epoch AI on to think about efficiency in AI. OK, so how are we getting inspiration for this? Well, in climate economics, there's this term called a negawatt. And the idea is you might look at your energy system and you say, we're actually going to increase our demand by 100 megawatts over the next few years. We're going to build capacity for 80 of them. And the last 20, we want to fill with negawatts. And what they mean by negawatts is we're going to invest in insulating people's houses or making our machinery more efficient and effective so that we don't need to increase our amount of energy that much. And I think this is actually a really, really important idea for us in this room and for the broader world, because for us, we're having exactly this question with computing. We're asking the question, what do we need to do to get to this next level of capability with our AI models? And we should think about, well, can we fill some of that with negaflops? And in fact, not only can we have been, and I'm going to show you that today. OK, so negaflops. A unit of compute saved as a result of conservation measures, such as improving the efficiency of an algorithm or software implementation. OK, so let's take a step back and think about the resources first, and then why this is going to be so important. So this is a graph produced by one of the former members of my lab, looking at AI systems over time. And what you can see is a huge change, right? Look at the scale of the y-axis here. And what you can see is from 1950 to about 2010, there was about a trillion-fold increase in the amount of computing that we were using in our AI models. It's a big increase. Most of that was driven by Moore's law. The pace of this line corresponds roughly with Moore's law getting better and our chips getting more efficient. But from 2010 on, there's a big change. We've had, in fact, this graph gets cut off. If you look more to today, you have almost another factor of a trillion since 2010 in the size of the amount of compute that we're using for these models. It's just enormous. So with such a large increase, we can say, well, we really like to get some of that efficiently. And of course, one of the ways we can do that is with better chips. And indeed, NVIDIA today is really right on the hunt for this. So this is a graph produced by one of my students, Emanuele. And what it's showing is the GPUs that are being produced by NVIDIA and how well they perform. And so you can see the different lines here. On the right-hand side, you can see floating point 16, 64, 32. Those are just measures of particular types of computations being done. And you can see that the compound growth rate of those things is about 60 to 70% per year. So that's even faster than Moore's law, right? We're improving these chips incredibly quickly. You can also see there the price is increasing, OK, and also the power has been increasing, but much more slowly. So that's good. We're getting more efficient in the hardware. But if you look at that trillion-fold increase I just showed you, this does not get us to that number. We cannot do this and keep our costs, our environmental damage, all of those things constant. So what do we need to do? We need to think about using the compute that we have more efficiently. So let me give you just sort of a very simple equation, which I use to help me think about this. So if we have some goal, we want to get tasks done per unit time. That's a very sensible thing for us to want to do. And we could say, well, I'm just going to take that equation and I'm going to divide the top and the bottom by computation. OK, so if I just spread that out, I get number of tasks per unit of computation and the number of computations per unit of time. Great. But that framing tells us that the right-hand side term is basically hardware speed, what we get from our hardware. And that other term is really about algorithms or the software implementation that we're doing. And what's exciting about that is that's a measure of efficiency. It says, I give you a certain amount of compute. Can you just do more with it? And as an economist, which is one of my hats, we love efficiency improvements, right? Productivity is something economists love. And what we see is that has a potential here to make a big difference. And what I'm going to show you is it does. So let's think about some very specific examples of this happening in the world. So each of these data points represents a large model being trained on a particular large language data set. And what you can see is at the far left-hand side there, you've got Megatron LM. So this is in the year where it came out, 2019. It achieved a certain level of performance. You say, OK, how long did we have to wait for other models to be able to solve that problem more efficiently? And what you can see with those other blue dots is that we were able to achieve that level of performance with much less compute overall. And in fact, by just before 2013, we're able to do it with a little bit less than 20% as much compute as we used in the first case. OK, that's a big change. And in fact, if you look at the doubling time there, that 14.9 months, that's saying that every 14.9 months, we halved the amount of compute we had to use to achieve the same level of performance. That's a big efficiency savings. But that's one example. What about GPT-2 when it came out? Actually, that also improved very quickly. We had new models that came out. They were able to achieve that same level of performance. And in fact, the doubling time there was 5.9 months. Very, very fast algorithmic progress. And more recently, we can see with Gopher, and again, we see a very rapid doubling time, 6.9 months. This is remarkably fast efficiency improvements going on much, much faster than we're seeing in hardware. Right? So when I said I think it's important for us to have this discussion, it's precisely because this is a huge contributor to how we're able to build bigger and better models because we're getting this greater efficiency. OK, so if you combine all of this analysis across all of these data points that we have, you can see this graph here. So what we have on the y-axis is the doubling time, and that green area represents the scope of what we see, and we see that the average doubling time is between about 7 and 9 months. So again, very, very rapid doubling of the efficiency improvements that we're getting. The other lines here represent work done by other people in my lab and by others showing the doubling times across other types of applications as well. And so you can see, for example, stockfish, computer vision, the average of textbooks. That's some work that we did in the lab looking across many, many different areas. And you see in many, many of these cases, you get this very, very rapid improvement in algorithmic efficiency. So I bring all of these up to say, first of all, it's just incredibly important that we take this into account, because what this is showing you is it's one of the main contributors. So let me now come to what this has meant in practice, because I said we were already using these negaflops. Well, what you can see in this graph is on the y-axis, we have the effective amount of compute, so how much compute you would have needed if you had scaled these models up using the same efficiency that you'd had at the very beginning. The blue area here represents the actual increase that we used in physical flops. And you can see 17 million X. So boy, we are indeed harnessing a ton more of these GPUs and the flops that they give us. But we've saved a factor of 22,000 by making our models more efficient. So for all those reasons, I hope we can bring into the vernacular the term negaflops, because I think it's actually capturing one of the most important drivers of AI, and one that people in this room and in many other areas are doing a lot to help all of us and to help the environment to do. Thank you.